Hello everyone. Today we are going to discuss a recent paper called Unsupervised Speech Recognition, also known as Wav2Vec-U. This paper was released yesterday, and this paper is a collaboration between Google and Facebook, the FAIR team. And the authors are Alexei Baevski, Wei-Ning Hsu, Alexis Conneau, Michael Auli. Alexis Conneau is from Google, and all the other three authors are from Facebook AI. So the paper is a bit lengthier paper. It is about 35 pages, and even the tutorials also is quite big. The overview is like this. We'll first see the introduction of the paper, then we'll see the overview of the model, just to understand what's happening. Then we will go into detail and start understanding what is self-training for semi-supervised ASR, which is a Wav2Vec 2.0 idea. Then we will see what is the unsupervised learning approach these guys are using, and what is the actual idea of this paper. Then we'll see some experiments and results. Okay, so as the name itself suggests, so the idea of this paper is about unsupervised speech recognition. So you guys might have heard of semi-supervised speech recognition or self-supervised speech recognition models, and Wav2Vec are one of the hottest topic right now in speech recognition area. And this Wav2Vec idea is not completely unsupervised. It uses something called self-supervised training to learn some basic speech representations, which you can fine-tune using some label data. And this you can look at it as a semi-supervised speech recognition problem, right? Because you're using a, let's say, small amount of label data and large amount of unlabeled data, and this works really well. In fact, there are many works which are done on top of Wav2Vec 2.0, and people have also shown that the Wav2Vec representations are so robust that they can be used for other applications such as emotion recognition and language recognition and so on. So today we are going to see something new, which is a completely unsupervised speech recognition. What that means is we are not going to use any label data. So there is zero label data, right? This is very exciting. I mean, if you can imagine, you can do speech recognition with no label data. You don't have to pay anyone to collect the data. Then it's amazing, right? So there are so many languages which don't have label data and they are low resource. You may be able to get some unlabeled data, and if you have such unlabeled data and if you can still build a speech recognition model, that is really cool, right? So we are going to understand this paper thoroughly, and the code is available in FAIRSIC library. You can just take the code and see and check it out and run it for your own languages and see how it's working. So what is the idea of this paper? So idea is to use self-supervised speech representations to segment some unlabeled audio data, so that you can map these unlabeled audio data to some representations which looks like phonemes, right? And then you can use adversarial learning to map the phoneme representations from the self-supervised model, and you have the actual phonemes from the text data, and the adversarial learning basically does this. I mean, you know about. I mean, many people knows about the generative adversarial network, right? So this approach basically uses some sort of a generator and discriminator approach to distinguish between the original samples, in this case original phoneme sequences, from generated ones. So that way the model kind of learns the phonetic representations. So that is the idea of the paper. We'll understand that in detail. So just note that the self-supervised speech representations here. So the self-supervised speech representations means you are using some sort of a pre-trained model which is trained in a self-supervised way, and the good one as of today, which many people use, is the Wav2Vec model, right? So Wav2Vec gives you really good speech representations. You can tap the contextual representations on top of the transformers, and then use those contextual representations, and those contextual representations kind of looks like a phonetic representation. So because they form some sort of a phoneme representations because of the quantization trick people use in quantization tricks used in Wav2Vec 2.0 paper. So we will see all those and we'll understand them in detail. And then so the paper shows that using these kind of speech representations from self-supervised model and this idea of this adversarial training, you can get the best unsupervised speech recognition WER on TIMIT, and the previous best one was 26.1, and the current this paper gets 11.3. If you can see, I mean the margin is the gap is quite large. I mean the results are really good, right? So we will see those. We will see the exact model architectures and so on in the result section. But I mean, I think the introduction itself shows that this model is really powerful and can be used for low resource speech recognition where you have no label data at all. And also they show some experiments on LibreSpeech, and they also experiment with other languages like low resource languages like Swahili, Tahar, and Sir, right? So let's look at the model overview. So the entire architecture looks like this, right? So this is the overview of the model. We'll understand this each block step by step, but this is how the model architecture is. So you have some unlabeled data. Assume, let's say you have a lot of audio recordings, right? Then you can take a Wav2Vec 2.0 model which is pre-trained on a lot of unlabeled data. It could be any of your favorite Wav2Vec model. You can use the large or base, or you can even use multilingual XLSR model, which it has representations for different languages. So if you are interested in building unlabeled unsupervised speech recognition model for, let's say, some of the Indian languages, so you can use XLSR model because it contains multilingual speech representation. So that way you can use any Wav2Vec models, any of your favorite Wav2Vec model which are available in FairSeek library for free, right? So you have unlabeled data, you have a pre-trained model. So what you are going to do is you are going to extract the speech representations from the Wav2Vec model. So what are the speech representations? So there are many ways to get speech representation. So you could simply use the feature extractors output, which is not so great. It has a lot of speech features, but they don't really have the phonetic representations. So but if you use the contextual network, so I am going to explain to you what is context network, what is feature extractor, and so on in the coming slides. But just assume I'm assuming you know Wav2Vec, and I'm telling you that if you have the Wav2Vec 2.0 model, you can look at the context network, which is this 24-layer transformer model, and you can tap any of those 24 layers. It could be last layer, it could be middle layer, and so on. And there is an experiment to show which layer is good for speech recognition. So I'm going to explain that in the coming slide. Just assume you are tapping some middle layer, and if you tap that, you get representations C1, C2, and so on, CT, assuming your audio has audio is some audio waveform and goes through feature extractor, and the feature extractor will give you some representations like x1, x2, and so on, xt. So these are speech representations, and these goes through context network, and the context layer output you are tapping is a sequence of vectors, right? Assume they are like 1024 dimension vectors, because that's the hidden dimension of the transformers. The output dimension of the transformer at every layer, right? So these are the vectors you are tapping, and these vectors you can cluster them using k-means cluster, right? So the k-means cluster, so the basic idea is like this. So the thing is, when you train Wav2Vec 2.0 model with lot of unlabeled data, so assumption is the model captures features like phonetic features, or it could be syllables, or it could be simple fast features, like which are the MFCC features. But as I said, if you look at any particular layer, which is one of them will be really good for phoneme classification, for example, let's say, right? And if you tap that layer and if you just try to cluster the vectors, the clustering will be really good, right? So assume you are doing 100 dimension, 100 means k means cluster where k is 100. You will get really nice 100 clusters, and those cluster you can assume them, or you can think of them as phoneme clusters, right? So this could be a phoneme a, and this could be a phoneme pa, and this could be phoneme, let's say, ta, right? So these are phoneme clusters, right? Now you can segment these phoneme clusters, right? So basically you can say, okay, the first 3 vectors belongs to phoneme a because they are all similar. Then the next 5 of them belongs to phoneme, let's say, some phoneme, let's say, pa, and so on, right? So you can segment these clusters if you know the cluster boundary, right? So that is also another problem. We are going to see how that is solved. So you have clustering, and you have segments into phonetic. You have segmented this C1, C2, C3, and so on to segments. Then you can build the segment representations, and for that you can use PCA and so on. We are going to understand it in the coming slide. So once you do that, so you get these segment representations. Let's call it as S1, S2, and so on till ST. Now these vectors, this could be of different dimension. This could be of 512 dimension if your PCA, whatever you are using, right? And these vectors you can feed it to a generator, right? So imagine, so whatever I explained till here, this is all just a Wav2Vec model and tapping the Wav2Vec model output, and then applying k-means clustering, then segmenting the data, and then something like PCA and getting the segment representations, right? Then comes the next part, which is the generative adversarial network, right? So this is the generative adversarial network, not completely, but there is this generator and there is this discriminator. So as you guys know, the idea of generative adversarial network is to it's like playing a game, right? So where the generator gives you something, and the job of the discriminator is to discriminate whether the thing which is coming from generator is actually is coming from the real distribution or it's from the fake distribution. So the fake distribution is obviously generator, and the real distribution is actually coming from the text data. So that is the next part. So assume you have till here you have segment representation, then you feed it to a generator. So the generator will give you some probability distribution over the the phonemes, right? So every segment you get the phoneme. What is the phoneme? Phoneme label. Let's say this is A, B. Let's say these are phonemes. Just assume, right? So you get these phonemes. These are distributions actually. The probability vectors, right? Now, as you know, okay, these are sequences of phonemes. But if you want to distinguish between this generated sequence of phonemes with the real phoneme sequence, you need some phonetic data, right? So what you could do is you can simply take some unlabeled text data, right? You can just crawl lot of unlabeled text data from web, right? Like if you are using some language which is let's say Swahili, so you don't have labeled data, you don't have to look for pairs of audio and text data. You can simply go and get audio data from some let's say news channel, and you can get some text data from some websites, right? So you take this unlabeled data and you do something called phonemize. So the phonemize basically takes every word and converts into phoneme sequences, right? Simple. You can do it with simple something called G2P, grapheme to phoneme converters. And once you get these phoneme sequences and you have the generated phoneme sequences, and the job of discriminator is to distinguish whether the input which it's getting is coming from the real distribution or fake distribution, right? So this way, when you train the model, when you update this generator and discriminator, so the generator will try to generate the phoneme sequences which are indistinguishable from the original or the real phoneme sequences. So that way you are actually getting the actual phoneme sequences. So once you get phoneme sequences, you can simply use some sort of a WFST decoder to decode the phonetic sequences into sequence of words, right? So for example, if you use Kaldi, in Kaldi you can build a graph, FST graph, which takes phonemes and gives you the words, right? So simple, like if you look at lexical FST, L.FST for example. So the idea is like that. So So this is the entire architecture. So so this is the overview, but I'm going to explain these things in detail anyway. So so as I said, so you have unlabeled data, you have unlabeled text data, unlabeled audio data, unlabeled text data. You process the unlabeled audio data, you process the unlabeled text data, then you train generative adversarial network. As simple as that, right? Okay. Now let's look at these things in detail. Let's understand what is the, I mean, whatever I explained to you is just overview, but we want to understand in detail, because let's say tomorrow you want to go and build this thing on your own for some very low resource languages. I think this is important. So first we will understand what is self-supervised training for semi-supervised ASR. In fact, the paper also gives you some introduction to classical or hybrid speech recognition systems, then end-to-end speech recognition system. But I'm going to explain only the self-supervised speech recognition systems because I'm assuming you guys will have some idea about what are hybrid systems and what are end-to-end systems. But the self-supervised system is pretty simple. If you look at Wav2Vec 2.0, it is a self-supervised or semi-supervised speech recognition model. So what they do is they use self-supervised learning, self-supervised learning using CPC laws to train a model which captures some audio representations. So the audio representations could be it can have good features like MFCC features, not exactly MFCC features, but some features which are very much useful for downstream tasks, right? And it may have phonetic information, it may have syllable information, and so on, right? So so that is the idea of building a self-supervised speech representations model, right? So the speech representation model, as I said, it's a Wav2Vec model. Assume it's a Wav2Vec model, and then you can fine-tune those Wav2Vec model for downstream tasks like ASR task. Then we'll see how do you choose the audio representations. As I said, you may not want to use the top layer always as the de facto or de facto layer for fine-tuning or to extract or to use it for the downstream task. You may want to see the capability of different layers, right? Because you don't know which layer which layer helps you or which layer gives you better representations for which downstream tasks, right? Because these models are black box models. You don't know what's going on inside these models, because we just feed lots and lots of audio data and then just expect the model to work, but we actually don't know what's actually happening inside the model, right? So this is just number crunching machines. We want to, if you want to understand them better, one way is to theoretically formulate the model and then building the model. Other way is to just build this thing and then start debugging, right? Debugging and understanding layer by layer what's happening under the hood, right? So that is the idea of choosing the speech representation. So you just examine the model so that you get the idea of which layer is good. Right. Then we'll look at how do you segment the audio signal so that you have the nice boundaries between different phonemes, and then we will see what is the pre-processing steps for the text data. Right. Okay. So what is self-supervised learning for speech recognition? So so if you have not heard about Wav2Vec 2.0, I think you should go back and see what is Wav2Vec 2.0 model, and I have a tutorial on Wav2Vec 2.0 model in YouTube. You can watch that, or you can just read some blog. There are many blogs because this is a very famous model. So the Wav2Vec 2.0 model looks like this. So what happens is, you have a feature encoder which is a simple 7-layer CNN. I'm assuming it's a large Wav2Vec model. So there are 7 layers of CNN. So the CNNs, they are 1D CNNs, and they take the raw audio waveform as input, as you can see here, and they build some latent representations for this audio waveform for every 20 millisecond, for example, right? So you get for this entire audio, you get some speech representation. These are vectors, right? So these are the features, and these features are quantized using quantization module, and these quantized representations are like this. Then you have a context network which actually takes these representations and then gives you the contextual representation C, right? So the C basically C1, C2, and so on, CT, they will have some hidden representations which are useful for downstream tasks like speech recognition. So usually when they fine tune this model, they just use the top layer directly, and they fine tune this context network by freezing this entire part, right? During frozen, right? During training or during fine tuning, they don't touch this part. They just try to modify, or they try to backpropagate through this context network, and everything works well. I mean, once you have pre-trained model, Wav2Vec 2.0 model, you just fine tune with small amount of label data and works really well. And these are like this works for not only English, they work for other languages, even with low resource languages, right? So even with just 10 minutes of data, they work really well. That's the beauty of this Wav2Vec 2.0 model. Now the question is, for our purpose, or for the purpose of unsupervised speech recognition, should we use this last layer contextual representations, or should we use something in between, right? So when I project this and look at this, so this actually is a 24 layer transformer model, right? So assume there are 24 blocks, and the input goes through here, and every layer does some transformation, right? And the last layer is what we are calling it as C. But this last layer may not be very useful for phoneme recognition, but some of the middle layers could be. So then an experiment is done to understand which layer is good for the phoneme recognition task, right? So for the phoneme recognition PER, right? So this is the Wav2Vec block ID. So you have, as I said, you have 24 blocks. And what these guys have done is, they have just taken this Wav2Vec 2.0 model and they have fine tuned it for phoneme recognition task. Not really fine tuning. They have taken one of the layer, and they have just tuned tuned the model only for phoneme recognition task, and they only use one layer representation at every time. So when they do that, and when they plot the phoneme error rate with respect to the number of layers, or with respect to the layer ID, they get this plot. This plot clearly tells you that at layer 15 you get a very low PER. So know that PER is the error rate, lower the better. So for layer 15 you get very low PER, right? And this is really good. So what we can do simply is, we can simply only use the 15th layer output, and we can just call them as the contextual representation C, which is equal to C1, C2, and so on, CT, right? As simple as that, right? This is for English, and for other languages, or if you have multilingual languages, the same thing also applies. So even for layer 15, you are getting very good phoneme recognition for other languages as well, like these languages, right? And before feeding the audios directly into the self-supervised model, you may want to do silence removal. So for silence removal, you can simply use some voice activity detector, open source voice activity detectors, and then remove the silence part, then use only the audio, only the non-silence part as input to the self-supervised model. But this is a really neat experiment, and I think there are a couple of other papers which also show this kind of idea, like showing which layers are good for which tasks and so on. But this diagram is really neat. So this shows that layer 15 is really good for phoneme recognition, and for the coming experiment, whatever you see, they are going to use this layers output directly, right? Okay, that is about choosing the speech representations for the task. Now how do you segment the audio signal, right? So when I say segment, you want to know the boundaries of the phonemes, right? So what you could do is, simply you take the speech, or let's say you do the silence removal, you get this audio signal, very small clip, let's say 2-second audio clip, and you just feed the audio clip through the Wav2Vec speech representation, Wav2Vec model, which gives you these the contextual representation C1, C2, and so on, right? Now this representation, what you could do is, you can do the same thing for all the audio clips, then you collect all the speech representation and you do k-means clustering, assuming k is 128, right? And you may imagine if you have a large amount of data, let's say for 1 second you get 100 vectors, and if you have, let's say, 100 hours, imagine how many vectors you get. So you need some very fast way of clustering these vectors, right? So for that they use something called Fast library, which has GPU integration, so you can do the fast clustering on the GPUs. And if you can install it using pip install Fias for Python 3.6, but if you are in Python 3.8, you can use Conda and install Conda install Fias GPU, so that it will directly install the Fias library, and you can do whatever you want or clustering on the GPUs if you have GPU, right? So what happens? So when you do the clustering, you can label each vector with a cluster ID, right? So once you do the clustering, you found out the cluster IDs, you have the labels for each CT, right? So T could be 1 to T, and you have the entire database. You can just label the entire data or entire database using this cluster ID, right? Now the boundaries, like how do I know the boundaries? Is very simple. Let's say you have 5 sequences or 6 sequences, and this is the ID 1, 1, 2, 2, 3, 3, let's say 3, right? So very simple. So the first 2 belongs to the phoneme 1, and there is a change here, and these 2 belongs to another phoneme, and these 3 belongs to another phoneme. Very simple. You just find the changes, cluster ID change, and you have the boundary, right? So boundaries are like this. This is 1, this is 2, and this is 3 segment, right? Very simple. Now after you do this, then you can compute 512 dimension PCA for all the speech segments, and that will be used as the training data for the generator. So we are going to see that in the coming slides. And also they use the mean pooling because we want to smooth the transition between the they take the average representation of the segment, so that so that is basically nothing but mean pool, right? So so this is the PCA part, and like once you do the PCA part, then you get the final output, which is S is S1, S2, and ST, and these are segment representations. So these could be 512 dimension vectors, right? So so once you get these segment representations, so note that the T here and whatever I showed you, T, they are same. Now we are going to see like how this is fed to the generator, and then you get the probability distribution of the generator output, and then you can do then you can get the phonemes probabilities by averaging the scores with the adjacent frames which are similar, and so on. We'll understand that in the coming slide, but this is the idea of getting the segment level representations. Now let's look at the preprocessing of text. So for preprocessing, it's very simple. You just have to phonemize the entire data. So phonemization is nothing but converting your text which are in the words and so on. You want to convert that sequence of words into a sequence of phonemes, right? So for that you have to use a G2P, grapheme to phoneme converters, right? So there are many G2P libraries available for different languages, and the one which is famous, or the one which is also used here, is called Phonemizer. So which is from Bootphone GitHub repo. You can just install it with simple commands, and then call this Phonemizer with whatever text file you have, and mention the language. It supports a lot of languages, and then you will get the phonemization, right? Very simple. Then they also do something called silence token insertion. So the main reason for silence token insertion is even though you do the voice activity detector, you are still not able to remove a small pauses, right? So for that, what you could do is you can assume, okay, there is still some sort of silence in the data, audio data, and you want to map all the frames which represent the silence into a silence phoneme, right? So how do you do that? You just insert, so you just make sure the actual the text data also has phonemes which are so phonemes which are silent phonemes basically, right? So, so that way you are making sure that if an audio is mapped to a silence phoneme and the text is also has a silence phoneme, then the adversarial training will be will be very smooth, right? So, so how do you insert the silence token in the text data? You could just insert in the beginning of the text and the end of the text, but that is not a very effective approach. You could what you could do is you can randomly insert with some rate, right? So as you can see here, they have plotted the rate of silence token insertion with the PER, and if you can see here, for 25% of the if the entire text has 25% of silence token, you will get the best WER or PER, right? And and you can see there are different. I mean, if you if you remove audio silence and compute WER, you will get very bad PER, and if you add silence token, you will get decent PER, and the baseline is 21, right? Okay, so that is all about self-supervised training and how do you get the audio, process the text data and process the audio data and so on. Now let's get into the real deal, which is the training of this unsupervised speech recognition model. We'll understand it in 3 sections. So first is model architecture, then we'll see what is the objective function, then we will see something called unsupervised cross-validation metric. Okay, so this is how the model architecture is. I think I also explained to you in the previous slide. Now the diagram is a little bit smaller. You have unlabeled audio data, sorry, unlabeled text data. You just phonemize this, and let's say you have a word, let's say hello, and you get phonemes h, hello, something like that. I am not really good at converting the words into phonemes, but anyway, let's say you get 4 phonemes, for example, and these phonemes you can convert them into 1 hot vectors, right? Because the number of phonemes will be, let's say, and let's say it's 60, and you can convert these sequence of letters into 1 hot vector, or you can use something like embedding and so on, but just assume you have 1 hot vectors for each of the phoneme for that word. Now you take the audio segment, do all the Wav2Vec processing and then highlights removal and everything. Then you get the segment representation. This is S, this is S1, S2, and so on, ST, right? Now you feed it to the generator. So generator is basically a simple convolution neural network. It doesn't actually change the dimension of, or it doesn't change the length of the text. It just does the convolution on every vector. Then you get to the output, which is the probability distribution over the phonemes, right? So this probability distribution or the dimension of this vector is O. If it is 64, I mean, if there are number of phonemes are 64, it's 64 here, right? These are the distribution. Now, like you can see here, the ST could be large, right? So if you have, let's say, 1 second audio, you'll get 100 frames. If your window is 10 millisecond, or if it's 20 millisecond, let's say you get 50 phonemes, 50 vectors, right? And you get distributions for 50 vectors here, but many of them will be similar, because the phonemes, let's say there are only 4 phonemes, and let's say every 10 phonemes or so 10 vectors are assigned to one phoneme, right? So you have to average these vectors based on the segment boundaries, so that you get one particular phoneme prediction, right? So so let's say you combine these 2 vectors and you get one vector here. Let's say these 2 vectors are written as it is, but like the idea is very simple. So you have the you have to combine the phoneme or the probability distributions which are similar to one another. Like for example, if these 3 adjacent ones have same probability distribution, then you can just average them and get one vector, right? So that way you are reducing this capital T, which is 50, to let's say 4, right? Now you have 3 vectors here, 3 vectors here. These are the phonemes. These are also the phoneme distribution. Then very simple, you feed it to a general discriminator, and then discriminator will decide whether it's coming from the real distribution here, or if it's coming from fake distribution, then you do the training. Very simple, right? Okay, like I said, like whatever I explained to you, the same thing is written here in text. You have generator G, discriminator C, and then the discriminator is trying to classify whether the samples are coming from generator, which are the fake ones, or it's coming from real distribution, which are actually coming from the unlabeled text data. Then the objective produces samples. The objective of the generator is to produce produce samples which are indistinguishable from the real ones. But the job of discriminator is to distinguish the originals from the originals, or the real ones from the fake ones, right? So this is like a game, right? So it's like a game of generator tries to fool the discriminator, but discriminator is trained in such a way that it does not get fooled, right? Very simple. Okay, like I said, it takes the generator takes segment S, which is a sequence of it's a segment which has length t, a sequence of vectors or segmental representations, and then they have to be mapped to m phonemes, and these are the phonemes and this distribution, like I said. And this is like whatever I explained to you in the previous slide, it's all written in the text here. So let's skip this slide. Now let's go to the objective. So the objective here is again is a, as I said, it's a min-max game. It's a generative adversarial network training. But the important part is, if you know about generative adversarial network, you don't have to worry about this loss, because it's very simple, right? So this is the main generative adversarial loss function. You have the generator loss, then you have discriminators, but the important ones are these three regularizers. So the regularizers are called gradient penalty, which is a simple gradient penalty introduced by folks in 2017 to smoothen the training of the generative adversarial network. And there is something called segmental smoothness penalty, and there is something called phoneme diversity loss. So let's look at this segmental smoothness penalty. So the basic idea of segment smoothness penalty is that you want to make sure that the consecutive frames are similar, right? Because like as I said, if you have 150 frames, and it's very likely that the ones which are next to each other are having the same probability distribution, because they are coming from the same phonemes, right? So because the 10 phonemes belongs to one phoneme, the next 10, for example, right? Like that, right? So for that you can use this penalty. So this is basically says the probability vector at time t and the probability vector at time t plus 1. If you take the norm, that loss that should be lower, right? So these two should be same, and this loss should be lower. So that's why you're adding this to the loss function with some scaling gamma, right? Okay, that is segment smoothness penalty. Then there is something called phoneme diversity loss. So the phoneme diversity loss says that you want to use all the phonemes, because it shouldn't happen in such a way that the model just tries to predict phoneme sequences for, let's say, 10 phonemes and just forgets about all the other phonemes, right? So that shouldn't happen. So for the diversity, basically tries to cover all the coverage. It's basically penalty for the coverage of all the phonemes. And how do you do that? You just compute the entropy of the distributions from the generator, and then you add it to this one. So why should it work? As you know, an entropy is nothing but the inverse of the information. So entropy is nothing but the average information, right? So for example, when do you get maximum entropy? Is when you have equal probability of all the outcomes, right? Like for example, if you have done basic probability course, you know that if you plot the entropy of a coin toss between 0 to 1, the probability of 0.5 where the coin is where the coin is not biased, and it's 50-50, you get the highest entropy, right? Why this happens? Because at 0.5 you never know whether what is going to happen, right? It's like saying tomorrow I may come, or I may not come, right? Or let's say tomorrow it's going to rain. Not a great example. Let's say some events which are which have very high surprise factor, right? So surprise factor because uncertainty, right? So if I say today I might come to lunch, come to dinner, or may not come to dinner, it's very ambiguous, it's very uncertain, and the information there is very high, right? Because the uncertainty is very high. So the probability is again 50-50. I may go or may not go, but the entropy is very high at that point. So this is just for the coin toss example. And the similar way, if you use all the outcomes with equal probability, then you get highest entropy, and there is negative here, so that way it's kind of, so this is the entropy, and then you add that loss with some scaling eta, and then optimize the whole objective. So that is about the objective. Now let's look at something called unsupervised cross validation metric. This is something interesting, and it's a bit tricky to understand. Even I had to read multiple times to understand it. So the idea of the simple idea is so the basic idea is very simple. You want some sort of a cross validation metric, so that for every epoch you want to choose the hyperparameters properly, right? So usually when we train any neural network, we know that we can monitor the loss function, loss values at every epoch, and then we can tune the model in such a way that you can reduce the loss. So choosing these hyperparameters again, it's kind of tricky unless you have labeled cross validation data. So usually we do that, right? When we are training any classification model, you take some sort of some validation set aside, and you use the validation set to monitor the models how the model is evolving, and then you just use those metrics to change the parameters such a way that the model kind of improves at every epoch, right? So the similar idea is the same thing applies here as well, but thing is you don't have labeled data, so you have to adopt something called unsupervised cross validation metric. So they do that in with the two quantities. One is language model entropy, and then using the vocabulary usage. So the language model entropy basically tells you that how good are the predictions in terms of perplexity, I would say, right? So what is the good metric for language model? Is a perplexity, right? So if you compute the probability score for, let's say, hello world, or let's say I am going to school, for example, right? I am going to school, for example, is if you compute the probability of this sentence, you will get pretty high number. Why? Because this is a natural sentence. But if I give you a sentence, I going school to, something like that, with jumbled words, then you don't get very high probability for it, because this is not a good this is not representing the language very well, so the probability of this sentence is very low. So that way, using this language model entropy and then vocabulary usage is a good metric, kind of to validate how good the phoneme generations are from the generator, right? So like I said, entropy serves as an indicator of fluency for a given transcription. Like I said, then it is measured with the language model probability trained on phonemized text data. Then the vocabulary usage again is a proportion of phoneme vocabulary being output from the model via Viterbi decoding. So measuring the vocabulary usage identifies the degenerate models which output fluent but trivial transcription. That's a good point. Now assume you do the Viterbi decoding from the transcript generated by the generator G for the unlabeled data X J, where J goes from 1 to S. Let's say you have 1000 segments, and this could be X1, X2, X3, and so on. You have 1000 segments, and for each segment you get probability distribution or sequence of probability distributions, and these are basically sequence of phonemes, right? After Viterbi decoding. And there are ns of them because there are ns segments, right? So entropy of the entire phonemized transcription is HLM of P, this P, and since they are independent of each other, so each phoneme sequences are independent of each other, you just compute the total entropy is just sum of all the entropies, right? Entropies of all the segments or sequences. Now for one sequence, it looks like this. So basically you compute the language model of at time step t, and you multiply by log of probability of, because this is a simple entropy equation, H equal to log of 1 over p, right? So this is the entropy equation, but since you have m time steps or m outcomes, you just multiply that. So why this is this negative is because if you can also write this as minus log p, because if you take log up, so it's minus. And but since you have multiple of them, then you can just write it like this, and this one kind of looks like this. Now, like I said, in the first step, we generate a phoneme transcription for a given training checkpoints. Training checkpoints means different hyperparameters, and the previously whatever I showed you is language model thing, and now it's the vocabulary usage thing. So you for a given let's say setting or hyperparameter or given hyperparameter setting, you could simply compute the vocabulary usage entropy p, and this u is nothing but the uniform distribution. And if you, let's say, you compute this p hat, and you can find out that the if the current whatever setting, it's less than the entropy of that current setting is less than the previous setting. So what you could do is you can just simply neglect that setting and then keep the current one. So like I said here, like it said here, in the final step we take into account the length of the transcription and the duration which satisfy the above constraint. Then we select the one which gives you the lowest sum, right? And I think this is the equation which takes care of the length of the utterances. So kind of bit difficult to understand because there are kind of multiple I mean the equation is a bit tricky to understand, but I think if you read multiple times we'll understand. So let's jump into the experiments. I think we're already close to 1 hour, so let's go fast. So the experimentation for phonemization, they just use this library, phonemizer library, and for models, so everything is implemented in FairSec library. Like I said, you also have the code for this. And for generator and discriminator, they use the Adam optimizer with beta 1, beta 2. These are the numbers, and then weight decay of this 1 e power minus 4. And so discriminator is trained with learning rate of 1 e power minus 5, and generator with minus 4. Then the total training steps are 150,000 steps. Then the training takes about 12 hours on a single V100 GPU, right? So for the convolution or the discriminator, composed of 3 causal convolution blocks with hidden size this much, and then receptive field of 16 segments. So for generator, non-causal convolution with kernel size of 4. The input to the generator, the segment representation S, like I showed you, S1, S2, and so on, ST, each of dimension 512, and the output of the generator will be of dimension O, which is the number of phonemes. So generator contains about 90,000 parameters. So we do not backpropagate to segment representations because we don't want to update the representations. We just want to use them directly from the Wav2Vec model. So these are some of the models. I mean, how the initialization of the lambda, gamma, and eta. They do something called self-training on top of this unsupervised training. So the idea is very simple. So you just take the pseudo labels from the unsupervised GAN model and then train HMM on top of it with pseudo label. Second, you can also relabel the training data with that HMM model and then fine tune the original Wav2Vec model using self-supervised training. So using CTC loss, right? That is noted as Wav2Vec-U plus ST. In the result section, I'm going to refer to this thing, this two-way or two-pass training of speech recognition model. And these are some of the settings. I mean, you can just go through them in the later in the paper. Now let's jump into the results section. So for the results, let's look at the WR on. So one more thing I think I forgot to mention. So the decoding is done using, like I said, FSTs. Because you are getting phonemes, you want the words, right? So you need to use some sort of FSTs which map the phonemes to words, right? So keep that in mind for decoding. So so for WR on LibriSpeech, dev test and so dev clean, dev other, test clean and test other, these are the numbers and comparison from previous approaches. Like you can see here, there are lot of supervised models, and the best ones, as you can see here, with language model, without language model and all. So as you can see here, the conformer model gives you the best. Not really conformer, depends. Both these two are kind of gives you the best supervised results for LibriSpeech. Going with semi-supervised training, as you know, Wav2Vec with noisy student training gives you the best WR. They even beat the supervised models. Coming to the unsupervised, if you just use Wav2Vec large, the results are not so good. I mean, the numbers are like 30 and 15 and so on, even with 4-gram LM and large supervised self-supervised model. But if you do the supervised, the self training plus the unsupervised training, then you get very close to the supervised models, right? Like 3.2 to 2. And so on, right? This is really nice. Coming to the TIMIT phoneme error rate results, you can see there is supervised training, then there's self-supervised, unsupervised, match setup, unmatched setup. So I'm going to tell you what is match setup, unmatched setup. But the supervised model is basically just build a supervised neural network with TIMIT training data, and for test you get this the results for test core test. For if you use self-supervised models with semi-supervised learning, with Wav2Vec 2.0 and then Wiki Wav2Vec, you get really nice results compared to supervised models alone. And there are other previous works which are done on this unsupervised training. In case of match setup, so match setup is basically using the transcriptions from the training data and then using the audios in the training data. Unmatched setup is where you just don't use the text data from the training data at all. So basically your text data is coming from completely different distribution and your audio is coming from completely different distribution. But in case of matched, you are using the text files and audio files from the same training data, right? Using that, there are multiple works done in the done previously with this GAN setup. In fact, this GAN setup is not so new. I mean, people have done this kind of experiment. In fact, I have a tutorial of this. I believe this paper, which is unsupervised speech recognition, and the results are not so good. I mean, it's okay-ish. Like 26% was what this paper was able to get with very large n-gram model. But if you use, in the case of match setup, if you use the Wav2Vec unsupervised and Wav2Vec unsupervised with self-training, you'll get the best WR. As you can see here, the numbers are like, the gap is like more than 14, right? So this is really good. So that is one. In unmatched setup, these models are not so good. I mean, they get really bad PER. In case of Wav2Vec, even with unmatched setup, the Wav2Vec self-training kind of works really well, right? As you can see here. Okay, good. So now let's look at multilingual speech recognition for multilingual unsupervised speech recognition. So there are many languages here. So I think German, French, Spanish, Italian, Portuguese, and I don't know what these languages, but there are many languages, and they can use this multilingual XLSR model. as the base model for the feature extraction. For extracting the segments or these the context representations. And with supervised training you get like really good WR. But if you use the unsupervised learning, not so good. Kind of a large gap between supervised and unsupervised, but I think this is still reasonable, I would say. Right. And what else? So we have for low resource languages, sorry about this, I don't know how to pronounce this language, but for this language KY and TT Tatar, so you have supervised training results, and then if you use XLSR and fine tune it directly, you get really good WR. And if you use unsupervised, it's reasonable numbers. And for Swahili, I think still reasonable. Kind of close to supervised learning, supervised results, but still there is some gap to cover. So that's all for this tutorial. Thank you so much for watching this tutorial. I think this tutorial was kind of a little bit lengthy, but so I think the paper was also kind of lengthy. So thanks so much for watching this tutorial. If you like this video, please give a thumbs up. Thank you.